Well, let us discuss the ideal AC circuits. Ideal in the sense that we will discuss here the AC circuit with pure R, AC circuit with pure C, and AC circuit with pure L, where R is the resistor, C is the capacitor, and L is the inductors. Now, if you see to the three diagrams, that R, C, and L respectively is connected to E equal to E0 sin omega t, which is the AC signals. Now, if you apply the Ohm's law to the pure resistors, you can write it as V equal to IR, and V being here equal to EMF, that is E equal to IR. So, therefore, E you can write down as E0 sin omega t, which is equal to IR, and that you can rearrange to write that I equal to E0 by R times sin omega t. And here, if you see that EMF expression, which is equal to E0 sin omega t, and I is I0 sin omega t. So, therefore, EMF and current are in phase, and accordingly, the phasor diagram we can represent as shown. And in the case of pure C, by definition of capacitance, you can write C equal to Q by V. So, therefore, here V being EMF, you can write C equal to Q by E, and rearranging you can write that is Q equal to C times EMF, which you can write down equal to C times E0 sin omega t. And if you are interested to find I, so you can differentiate it. So, therefore, I equal to dq by dt, which is equal to d by dt of C times E0 sin omega t. So, therefore, C times E0 being constant taken outside, the derivative of sin omega t is omega times cos omega t. So, therefore, your I, which is equal to omega times C times E0 times sin omega t plus pi by 2, because you can write down cos omega t equal to sin omega t plus pi by 2. So, therefore, here I you can write down equal to E0 upon 1 upon omega C times sin omega t plus pi by 2, and 1 upon omega C is x with subscript C, that is your capacitive reactance. Xc is your capacitive reactance, and I0 times sin omega t plus pi by 2, that is equal to I. So, therefore, we see that unlike the case of resistor, here E equal to E0 sin omega t and I equal to I0 sin omega t plus pi by 2, that is EMF is lagging behind the current by pi by 2, and accordingly the phasor diagram you can see that the EMF is lagging. If you see to the pure inductive circuit, you can write the EMF expression for inductive circuit at any instant, that is E equal to LdI by dt. You can rearrange this expression to write that is E dt is equal to LdI, and you can simply integrate the di expression to get the current, that is 0 to I. So, E by L dt 0 to t, which will give you E0 by L times sin omega t dt plus E0 by L being constant taken outside. So, I equal to E0 upon L times integration 0 to t sin omega t dt. And if you integrate sin omega t dt, you will get minus of cos omega t by omega. So, therefore, the I expression you can rearrange it to write that is E0 by omega L times sin omega t minus pi by 2. If you see, unlike the case of resistor and capacitor, the EMF expression equal to E equal to E0 sin omega t, and current is I equal to I0 sin omega t minus pi by 2. Here I0 is equal to E0 by XL, and XL being the inductive reactance. And here if you mark EMF ahead of current by pi by 2, and accordingly the phasor diagram we have represented that the EMF is ahead. If you compare the three cases of current and EMF expression for AC pure R, AC pure C, and AC pure R, you can represent it in a diagrammatic manner as shown. And for your calculation of power, which are useful for certain problems, you can have your power calculation for pure R, which is equal to P instantaneous, which is equal to V instantaneous times I instantaneous. So, therefore, V instantaneous is nothing but E0 sin omega t, and I instantaneous is I0 sin omega t. So, therefore, instantaneous power, which you can write down equal to E0 I0 times sin square omega t. And if you are interested for average of AC power consumed, that you can take the average of this E0 sin I0 times sin square omega t. So, therefore, average power consumed, which you can write down average of P equal to E0 I0 times average of sin square omega t, and average of sin square omega t means 0 to 2 pi integration of sin square omega t dt, which will give you half. So therefore, average power is equal to E0 I0 times half, which you can rearrange to write as E0 by root 2 times I0 by root 2, and E0 by root 2 is nothing but ERMS, I0 by root 2 is nothing but IRMS. So therefore, average power consumed in pure resistive circuit is nothing but ERMS times IRMS. But if you see to the other two cases, that is pure C and pure L cases, that the average power consumed for these ideal circuits of capacitive and inductive, it is 0. We will discuss more of this AC and its applications in our subsequent class. Thank you.